Hi guys and welcome back. Today we're going to be doing the Doppler effect. Let's get straight into it. So we've got an example question here called, let's read it. It says, what is the frequency heard by a person driving at 15 meters per second toward a blowing whistle at 800 hertz? And it gives us the speed of sound. So we're given three things. We're given two velocities, and this is actually in meters per second. Should have written that. I was right now. ms -1. And yeah, so we're given two velocities and one frequency. So the equation we use for the Doppler effect, or one of them at least, is if the frequency or the apparent frequency equals the real frequency times the velocity of the wave divided by the velocity of the wave plus minus the velocity of the source. So what does that mean? We've got the velocity of the source is the speed of sound. Is how fast the observer is moving, how it's relevant to our F, our apparent frequency. And our velocity of the wave is just the speed of sound, and if you're not given the speed of sound, you can safely assume that it's 340 meters per second. Forget the 6, that's just in this example question. So we can get started. The first thing I always do is list all the known variables. So what have we got? We've got the speed of sound, which is the velocity of the wave, so VW equals 340 meters per second. The velocity of the source, which is given as 15 meters per second, and we're given one frequency, and this is the real frequency. This is this F here, and this F over here, the apparent frequency, is what the person hears, because the actual frequency and what a person hears changes. So if you hear a car coming towards you while it blows its horn, it's going to sound high pitch, and then as it drives away, it's going to get lower pitch. It's going to go, and that's noise. That's the stereotypical car driving towards you then driving away sound that we all know and love. So the frequency, this given frequency is the genuine frequency, and that's 800 hertz. Great, we've got everything. So what's going to happen here? Do we use plus or minus? And how do we know what to use? Well, if it's moving toward you, then you use minus. If it's moving away, you use plus. And the reason exactly for that, it's a little bit complicated, but you just need to know that the frequency is going to be higher if it's moving towards you, and the observer could expect a higher pitch, as I just, with that sound of the car analogy that I just did. So in this example, the person is driving towards a stationary factory that's emitting a sound, and this man over here, if he was stationary, would just be receiving the sound at the same speed of sound. That would be at 340 meters per second. But he's not, is he? Because he is moving in this direction, so we can forget about that. He's moving in this direction, and that means the waves coming towards him are going to be compressed, and he's going to be hitting each wave sooner, hence increasing the pitch of the sound, hence increasing the frequency. So enough of that, let's get on to plugging in the variables. So let's do it down here. So we have the F is what we're trying to calculate, so there's no need to rearrange at this stage. The F apparent is what we're trying to calculate, times 800. Remember, we're just looking here to see what to do, and then times the velocity of the wave, which is 340.6. We can just look up there to remind ourselves. I didn't write a 0.6 there, but it's okay, it's the same thing effectively. Divided by 340.6 minus, because we're moving towards the waves, minus the velocity of the source, which it's a bit of a trick question, but in this case it is the car, which is at 15 meters per second. So minus 15. And when we equate that, we get 836.8 hertz. So what do you notice out that? Well, you should notice that that number is higher than this number over here. So the man is hearing a frequency that is louder than the actual frequency. He is hearing a higher pitch, and that's because he's compressing the waves. So that's the key point to take from that, besides how to do the equation. He's moving towards it, so he'll hear a higher pitch because the waves are compressed. Alright, let's move on to a slightly harder question. The car analogy again. This car's driving towards a man while blowing horn at 450 Hertz. The man detects 470 Hertz. That's meant to say how fast is the car moving, and it gives us a slightly altered speed of sound, 343 meters per second. So what's it given us? It's given us the speed of sound, and it's given us two frequencies. So the only thing that's left, if we do our equation, so I'll just quickly do it up here, F equals F velocity of the wave divided by velocity of the wave, and the plus minus, and once again the wave's being compressed because they're moving towards the source, or the source is moving towards the observer, so it's minus once again the velocity of the source. So what are we given? We're given the frequency, the detected frequency. We're given the actual frequency, which the man detects 470 Hertz. The actual frequency is 450. So that's how you can tell that it's moving towards him straight away, because the man's hearing a higher frequency than it actually is. So, and we're given a velocity, and the velocity is the velocity of the wave, which is in this case 343 meters per second. But once again, if you're not given it, assume 340. Alright, so we've got, what do we have? We've got this, check. We've got this, check. We've got this, check, which is the same as that. So we don't have this. So that's what we're going to need to get. We need the velocity of the source, as the question implies. How fast is the car moving? So what's his velocity? And this equation as is will not be able to give us that. We're going to have to do some rearranging. Hopefully you know how to rearrange. I'm not going to go over it now. I'm at the stage now where I don't need to rearrange. I just know what the equation will be off by heart, because I've done it before. I've just memorized it now. So the velocity of the source equals what is it? Equals the actual frequency times the velocity of the wave minus the apparent frequency times the velocity of the wave divided by negative apparent frequency. and you'll know it's negative if you actually rearrange it. That's just how it ends up coming out. So once again, rearrange it. If you can't rearrange it, just memorize the formula. So that's pretty much what I've ended up doing. I could rearrange it, and I'll just have to actually do it. It's better to just remember it. So, great. We've got our rearranged formula. Shall we plug in all the numbers? Yep. Okay. So, just give me some more room over here. So, we are given... So, it's the actual frequency times the velocity of the wave. So the actual frequency is 450, so 450 times 343 in this case, minus the apparent frequency, which I believe is 470, just double check that, yeah, 470 times the same thing, 343, velocity of the wave, divided by negative velocity of the wave, once again, 343. Great, so we plug that in. What do we get? Running out of room here. Well, we end up getting 14.59 meters per second. If you got that, great. If you didn't, well, just try again, memorize the rearranged formula, and that's what you should get. Yeah, great. Cool, so that's all for now. What I'd recommend that you do if you're trying to learn this is try to do both of those questions again. Pause it at the point where I state the question, and then attempt it by yourself, and if you can't get it, then watch the walkthrough. Alright, thank you very much. If I could just stop the recording.